Hey guys, thanks for joining me on CodeQuest. This is Sanjit, and this channel is going to be all about data structures and algorithms. And this video series is pretty much concentrated on graph algorithms. And this video, we're going to go through Dijkstra's algorithm. So, in order to have any kind of understanding, a strong understanding on any kind of graph algorithms, it's pretty much required for you to have a basic knowledge of all basic graph concepts, things like adjacency matrix, uh, basic definitions, adjacency list, and all that. So if you don't have any kind of knowledge on all those, don't worry. I'll be putting out a video on those uh, down this week most probably. So assuming that you have knowledge and all that, let's continue with this video. So what's Dijkstra's algorithm? Like what's single source shortest path algorithm? So as the name suggests, single source shortest path algorithm tries to find the shortest possible path between given source node and every other node in a directed or undirected graph. Okay, so that's it. So the algorithm may kind of vary slightly based on whether the graph is directed or undirected. Otherwise, the algorithm is pretty much the same. So if you didn't know, undirected graph is nothing but edges do not have any direction, and the weights of an edge is same regardless of which direction it is traversed. This means that when applying Dijkstra's algorithm to an undirected graph, it is not kind of necessary to keep track of the direction of the edges. Uh, uh, while uh, as in a directed graph, the edges have a direction, and the weight of an edge may be different depending on which direction it is traversed. For example, how should I put this? Like let's say an edge, like let's have two nodes, vertex A and vertex B. May like from vertex A to vertex B, the edge might have a weight of 2, while from B to A it might have 3. So this means when applying Dijkstra's algorithm to directed graph, it is much more important to keep track of the direction of the edges. So we have to pay attention to direction when it comes to directed graph. So as simple as that, Dijkstra algorithm is kind of a greedy algorithm that solves the single source shortest path algorithm, shortest path problem for directed or undirected uh, graphs with especially non-negative weights for edges. One of the drawbacks of Dijkstra's algorithm is negative weights. We'll look into that later in this video. So let's continue into the problem actually. An example algorithm. So here's a graph. As you might know by now, all these blue circles here, um, sorry, yeah, all these blue circles here are nothing but nodes, and these lines are edges, and the numbers that they've given here are nothing but weights of those edges. Okay, so it's as simple as that. So how do you solve this? Like this algorithm is nothing but, as I said, you're just going to find the shortest path between source node, and any node can be considered as a source node, uh, between source node and every other nodes in the graph. Okay, so that's the thing. So you're going to find the shortest path between the source node and every other every other node in the graph using this algorithm. Okay, so initially, what you're going to do is you're going to assign uh, distances, uh, like to every node. You're just going to assign distances from the source node actually. So let's look at that. So here's uh, a, a graph. So here's the thing. So the distance for of the source node from itself is 0, right? Yeah. So there's no distance between the source node and source node itself. So we have 0 here. And what we're going to do is we're going to assume that every other node in the graph is at a distance of infinity from the source node. Okay. So this is going to help us to solve the problem. So what you're going to do is you're going to assign this the distance between source node to the source node as 0, 0, and the rest of the nodes as infinity. So here's the thing. What you're going to do is you start with the node. Okay, you start with the node and check like uh, whether whether you can reduce, uh, how should I put this? So what you do is uh, you're going to update its neighbors. Okay, so if their shortest path uh, from the source node can be like improved or reduced by going through this current node that you have at your hand right now. So that's how it works. Like, so you have zero, right? uh, to the source node. So what you're going to do is you're going to check its neighbors. Okay, so what's the shortest path that you can take to this node? Actually, it's infinity, but you have a weight of 4 here. So what you're going to do is, so guys, let me give you an set of formulas. So here's the thing. So always remember, let's say let's say current node is K. Yes, then sorry for the handwriting, guys. It's really bad. I don't have a pen or anything like that, so it'll be kind of really bad. Let's say current node is K. What you're going to do is, if you want to update a node, you're just going to check this. Okay, the current node's value plus uh, the edge. Okay, E stands for edge from current node K to the next node. Guys, really sorry for this handwriting thing. Maybe I'll do it again. Yeah. Let's say the current node is K plus uh, the edge weight. So edge between from the current node to its neighbor. There can be n neighbors. So what I'm going to do is I'm going to put n of I. So it's nothing but k plus e of k to n of I. So this represents the edge where n of I is going to be the set of neighbors of k. Sorry about that. My handwriting is really bad. There's going to be nothing but set of set of all neighbors. That's it. Okay. So I'm just putting a set right there. Okay. So set of all neighbors. So for this node here, the set of all neighbors is this node and this node. That's it. The nodes that are directly connected to it. Okay. So these are its neighbors. So what you're going to do is you're going to calculate this and check whether is if this value is less than the value of that node uh, right here. Okay. The value of that neighbor. Okay. So what you're going to do uh, is it less than that neighbor? Okay, n of I, the set of neighbors. Okay, so that's what you're going to check. Okay, so let's do it right here. Okay, so this is the thing. So current node K, uh, that's what I've given the name for it as. So plus the edge weight of K to set of neighbors is less than the set of neighbors. The set of neighbors I've given in subscript I to denote the n neighbors of a given vertex. Okay, so what you're going to do is uh, you're going to check whether this value is less than the current value assigned to that node. Okay, if it's lesser, you're going to reassign this calculated value to that. Okay, so let's see how it works. Okay, so here you have 0, right? Yeah, so what you're going to do is, so this is k, you're going to add 0 plus from this node to this node, what's the edge value? It's 4, right? So 4. So you have calculated the left hand side, which is k plus edge of k to, really sorry about the handwriting, guys. Ni is less than ni. Yeah. So whatever. So so this is the thing. So the current node is 0. So the current node is this node. So its value is 0. Uh, value means the distance from it to the source node, which is 0. So this is the source node, it's 0. And the edge weight from 0 to This node is 4, so we have given 4 here. And and the value of this node is infinity, right? So what we have initially assigned is uh, infinity as the we have assigned infinity as the distance from the source node for this node. Okay, so what we are going to do is we're going to check whether that this value is less than infinity. And yes, it's less than infinity. So what you're going to do is you're going to assign 4 here. Okay, so this node is going to be 4. Okay, so what you're going to do is now, once you have done with one neighbor, and now you're going to go for the next neighbor. Okay, so so this node has only one neighbor left. Okay, so this one. So again, you're going to do the same. So the current node 0. Okay, plus the edge weight. So from this node to this node, what's edge weight? It's 4. And what you're going to do is you're going to check whether that is less than the value of this node. Okay, is it less than the value of this node? Yes, absolutely. This is 4 and this is infinity. 4 is less than infinity. So what you're going to do is you're going to assign 4 here. Okay, so this is the thing. So uh, now you have visited all the neighbors of this node, source node. So you're done with the source node. You're not going to visit or touch it again at all. So remember this really well. Once you're done with the node, after visiting all its neighbors, you're not going to touch it at all. Okay, so that's it. The you're not going to come back to this node at all. So this is a for for this node, the shortest distance, the shortest path is this one. For this node, the shortest path is this one. Okay, so now now what we have to do. So once we have visited this node, uh, we have uh, we have to check uh, the shortest path for other nodes as well, right? So what we're going to do is we have the neighbors of this node, right? Like all the nodes that we have visited right now from this node. What you're going to do is you're going to choose the node with the minimum value. Okay, you're going to choose the node with the minimum value from the entire graph. Okay, so let's change the slide actually. So here it is. So yeah, so now we are going to choose the node with the minimum value in the entire graph. So we have two nodes, 4 and 4. You can choose the rest are infinity actually, and this one is actually visited, so you can't choose this one. Okay, but you can choose any of these 5 other nodes. Okay, 1, 2, 3, 4, 5, and you have to choose the node with the minimum value. These 3 have infinity and these 2 have 4, and you can choose any one of these. So let's say I'm choosing this one. So what you're going to do is now you're going to visit all of its neighbors, unvisited neighbors, all of its unvisited neighbors. So let's see. Let's write that formula again here. The current node. I'm again sorry about the handwriting. It'll be like pretty bad. I don't have any kind of device for this thing. Sorry. So this is k plus e of um, current node, right? From current node to set of all other nodes is equal to less than set of all other nodes. Sorry. Okay, so if you can't understand this formula, I'm just telling this is current node plus the edge weight from the current node to all its neighbors, set of neighbors, denoted by I. Uh, if it's less than this or its current value, uh, then if it's less than the neighbors, this set of neighbors' current value, you're going to assign the calculated value. That's it. So now you're at this node. Okay, this node. Okay, so what are its neighbors actually? So the source node is a neighbor, and this other node is a neighbor, right? So the source node is visited, so you're not going to touch that. Okay, so leaving that node apart, you just have one node left here. Okay, so this is the node that you have to concentrate on. So let's do the thing. So what you're going to do is current value, which is 4. You have 4, right? Plus the edge weight from the current value to that node, which is 2, as you can see from this value. this node to this node is 2 actually, and you're going to check whether this is less than the value of that node that you're trying to you reach. Okay, uh, is it less than that node? Is it less than 4? No, right? Since it's not less than 4, so what you're going to do is you're going to retain this value 4. Okay, you're not going to change it to sets, you're going to retain it, its value as 4. Okay, only if it's uh, less than the current value you're going to change. Okay, so as you can see now, if you have visited all the neighbors of this node actually, yeah, because this node is already visited, you can't go there, and now you have visited this and tried to update it, but you couldn't because this was much better. Uh, this path is much better than this path. This path is longer than this. So what I've done is you've decided to retain the value. So you have visited this node as well. Now you can't touch this node. Now you have to find what you have to do is, now you have four nodes left, right? You have to find the node with the smallest value. Okay, like the shortest distance from the source node, the node with the shortest distance from this source node, and uh, start this process again, like reiterate this process. Okay, so let's go to the next slide actually. Yeah. So as you can see, you're trying this node actually. You're trying with this node and checking whether this distance is smaller than the current distance of this node. Like 4 plus 2, is this smaller than 4? No, it's greater. So you're not changing that. That's the same thing as I told before. Okay. So now let's come here. Yeah. Okay. So right now, let's go back actually. So we are at this node currently. Okay. We are at this node. Let me write this formula again for you people. K plus, I'm sorry about that. Uh, it, it always comes like that. I'm really sorry about that. A pretty bad handwriting, like and I don't. So edge from K to set of all neighbors, that's Ni. Whether it's less than Ni, then you're going to assign that value. That's it. Okay. So let's see. Now we are at this node. Okay. This node. Okay. So yeah. So what we're going to do is we're going to take all its neighbors. Okay. What are the neighbors of this node currently? Okay. So you have this node has around like literally five neighbors. Okay. This one, this one, this one, this one, and this one. Yeah. Because you have a direct edge here, direct edge here, direct edge here, direct edge here, direct edge here as well. So this node kind of has five neighbors. So what you can see is already we have two neighbors that are visited. So what you can't do is you can't go and try to visit this neighbor again. Okay, well, uh, like you can't try to update it. Okay, so it's completely gone. You can only check with these three neighbors. Okay, so let's do this. Okay, so let's start with this neighbor. Okay, so what you're going to do is you're going to check this. Okay, so what's the current value? The current value is 4. Okay, edge from the current value to a neighbor ni is 3, in this case 3, because the edge from this to this is the cost is 3, or the weight is 3. So what you're going to do is you're going to add 3 and check whether this is less than the value of that node. Is this less than infinity? Definitely yes. So what you're going to do is, so this is 7, right? So what you're going to do is you're going to change this to change this to 7. Okay, so yeah. So once this is done, you have visited this node. Okay, so this is the shortest distance from for this node from the source node. So you have 4 here, 4 plus 3, 7. Okay, now what you're going to do is again what you're going to do is you're going to go to the next neighbor of this node, which is this one. Okay, and now you're going to check this condition again, whether uh, whether you can update the shortest path to this node from the source node. So what you're going to do is the current value is 4, right? And the edge value from 4 to this node is sets. So you're going to add sets and check whether that is less than infinity, right? Yeah. So yes, it is less than infinity. 10 is less than infinity. So what you're going to do is you're going to change this value to 10 essentially. Okay, 10 essentially, and it's done. And again, sorry, this is 10. If you can't see it, yeah. So this is done, and what you're going to do is uh, you're going to visit the next node. Okay, okay. So the next node is this one. So again, you're going to check the condition. So it's going to be 4 plus what's this value? The edge value is 1, and check whether it's less than infinity. Yeah, it's less than infinity. So what you're going to do is you're going to update it. Okay, so it's going to be 5. Yeah. So what I've done is you visited all the neighbors of this node, okay, and updated its weights. So uh, what I've essentially done is visited all the neighbors of this node, right? So you're done with this node. So this node is visited, and you're never going to touch this node again at all. Okay, okay, yeah. So if you go to the next slide, yeah, can you see this? You have 7, you have 7, 5, 10, and you have 7, 5, 10, right? Am I right? Like so. Now all these nodes are actually visited. I'm really sorry about this handwriting. It's really really bad actually. Okay, so what you're going to do is you're going to find the shortest. Again, you're going to find whether choose the node which has the shortest distance from the source node. So which node has the shortest distance from the source node actually right now? This one, right? So this is around like 5 from the source node, this is 7 from the source node, and this is 10 from the source node, right? So you're going to start with this one. So this is the current node right now. Okay, so what you're going to do is again, you're going to check all its neighbors. This node has only one neighbor left because this neighbor is already visited, and you can't touch that. But this neighbor uh, is is kind of there. You can now you can apply the formula that I told you before, which is current node plus edge from the current node. Sorry about that. It's kind of really bad. I'll write it again. Sorry. Current node plus edge from current node to neighbor list and neighbors. Okay, done. So here's the thing. You have visited all these 3 nodes, and you have chosen this node as the next node to start with. So what you're going to do is you're going to check all its neighbors. This one is already visited, you can't do anything about that, but you have one left here. Okay, so what you're going to do is you're going to take the current value, which is 5, and add it with the uh, edge value, which is 3, right? The weight is 3 to that node. Okay, and you're going to check whether that is less than the value of that node. The value of that node is 10. We updated it last time, right? So it's 10. It's not infinity this time. It's 10. So is 8 less than 10? Right. It's less. So what you're going to do is you're going to change it to this thing. Okay. So it's going to be 8. Okay. So that's the thing. So now this node is kind of visited. So you're not going to touch this node again. Okay. You're not going to touch this node again. And uh, what you have what you have left is these 2 nodes which you have to visit right now, which you can visit. So once this is done, as you can see, this is 8, right? You have changed it to 8. Okay, so here's the thing. So once this is done, sorry for that. Okay, yeah. So what you're going to do is, this is visited, right? This is visited, this is visited, this is visited, and this is visited as well. Remember, for some reason this is given in this color. Actually, in my problem, I haven't done that yet, so maybe I'll continue here itself. Actually, that's better. Actually, yeah. So let's consider this is visited, okay, and this is 8, okay, and this is visited as well. Yeah. So you have two nodes left. Now we are going to check which node has the shortest distance from the source node. Okay, so uh, the shortest distance is 8 or 7. Oh, okay, it's 7, right? Yeah, it's 7. So what you're going to do is, you're going to apply the formula as usual. So every node of 7 is visited except uh, 8, right? So this node which I've changed to 8, every other node is visited except this one. So what you're going to do is, you're going to do this 7 uh, plus 2, which is the edge from this node to this node. Okay, yeah, and you're going to check whether this is less than 8. Is it less than 8? No. 9 is greater than 8, right? 9 is not less than 8. Yeah. So you can't, you're going to retain this value as 8. Okay. You're not going to change it to 9. Okay. So that's the thing. So now what you've done is, you've visited this node as well. Okay. Because all its neighbors are already visited. It has just two neighbors, 4 and this one and this one. This is already visited, and you just visited this one now, and you try to update it to 9, but it has a value lesser than 9, so you're not going to update it. You're going to retain the value 8. Okay, so this is done. So as you can see here, you visited all these nodes. The only node that you have left right now is this one. Okay, so the last node, and this when you go there, so here's a calculation for that, the thing, when you try with 7, you get 9 less than 8, and you're not going to update it. So here's the thing. So when you reach 8, when you reach 8, you're going to check all its whether all its neighbors are visited. As you can see, all its neighbors are already visited. 7 is visited, and 5 is visited, and 4 is visited. Yeah. So it's already done. So you can't do anything with this. So you're going to make it visited as well. Okay. So what you end up with is the shortest path for every other node in the graph from the source node, right? First, the shortest path for this node from the source node is 4. The shortest path for this node from the source node is also 4. The shortest path for this node from the source node is like 4 plus 3, and it's 7. The shortest distance. I'm sorry. And for this node from the source node, you have the shortest path as from 0 to 4 and 4 to 5, like this. So you have the value is 5, like 4 plus 1, 5. And the shortest path for this node from the source node is through this node, sorry, through this node, and here. Okay, so what you have is 4 plus 1, 5, plus 3, 8. Yeah. So here's the thing. This algorithm is called single source shortest path algorithm. Now this algorithm has a drawback. So this is one of the a simplest example I've given you, and it's with undirected graph. When it comes to directed graph, you're just going to have the edges, the direction of edges in mind. Okay, it's pretty much the same. What you do is, if a direction is given, sorry, it changes and show you. If something is directed like if this edge is in this direction, what it means is 8 is a neighbor of 4, but 8 is 4 is not a neighbor of 8. You have to consider it that way. In undirected graph, you consider everything as, if it has a direct edge, if it has a direct edge, you just consider it as a neighbor. That's it. In undirected graph, that directions are sorry. In directed graph, directions are important. That's it. So this algorithm doesn't work with negative edges. Let's see why actually. So I have an example ready for you here. So as we have seen, what initially what we'll do is, uh, see, right here you have a negative edge. Okay, so let's start this problem. Initially, what you'll do is, considering this node as a source node, what you'll do is you'll assign 0 here, infinity, infinity. Now you start with this node. Okay, so what you do is you add the kind of value of current node. So if you see here, this is directed. See, you have the direction. Okay, I'll say you how it works. I'll tell you how it works. Sorry. Uh, yeah. So here's the thing. Uh, the current value plus the value of the value of the sorry, the weight of the edge to the neighbor, which is 2. To b it's 2. Okay, and you're going to check whether that is less than infinity. I'm doing for this one. It's less than infinity, so you're going to assign 2 here. Okay, okay, and here similarly you're going to assign 4 here, right? So what this essentially becomes is, this one becomes 2, this one becomes 4. Now, generally actually in Dijkstra, what you'll do is you're going to select now as this is visited already, you're going to select the next node. Okay, okay, you're going to select the next node which has the shortest distance from the source node, which is B, right? It has a value of 2 and this has a value of 4. 2 is the shortest from the source node, so you're going to select B. If you go to B, if you check it, it doesn't have any neighbors. It's important to understand this. This is a directed graph, right? So it doesn't have any outgoing edges. This means it doesn't have any neighbors. Okay, uh, it has two incoming edges, but these are neighbors of. So what it essentially means is, it kind of C has a neighbor of B and A is neighbors B and C, but B doesn't have any neighbors. Okay, so what you're going to do is you're just going to visit it and get that's it. It's done. So it's set. So the shortest path is 2. Okay, now you can never visit this node. Okay, that's it. But when you come to C, when you come to C here, uh, you have one neighbor, right? That is B. Yeah, but it is already visited and has the shortest distance, shortest path assigned to it as 2. But the reality is the shortest path is going to be 4 plus the edge minus 3. Yeah, and whether it's less than 2. I'm sorry, this is 2 actually. So it's going to be less than 2. It's going to be 1, essentially, which is less than 2. So this should be 1, but you can't do that because this is already visited, and you can, once a node is visited, it can't be visited again in Dijkstra's algorithm. So this is the major drawback when it comes to negative edges. Okay, so that's it with Dijkstra's algorithm. Mm, So if you have any kind of doubts, you can comment me. You can ask them in the comments, and yeah, that's it. So I'll show you implementation of Dijkstra's algorithm in Java soon. So I hope you'll be waiting for that. Yeah, thank you.